that in your work you can design, model, review, and manage with confidence. This also means that we strive. Hello, and thank you all for joining us today for this educational Innovise webinar. My name is Caitlin Nyan, and I'm part of the marketing team here in the Innovise Portland office. In this webinar, we'll discuss how you can take the guesswork out of designing and analyzing sewer systems in a climate of change. For those of you who may not be familiar with Innovise, we have a long history of providing high-performing, innovative software solutions. Our intention is to make sure that in your work you can design, model, review, and manage with confidence. This also means that we strive to provide excellent customer service and support, and that we offer continuing education opportunities like these for engineers and others in our industry. Innovise offers a library of software programs for the design, analysis, and management of water infrastructure. Now, on with our presentation. I'd like to introduce our presenters. Today's presenters are Matt Anderson, Anthony Hooch, and Carolyn Rose. Tony joined XP Software, now part of Innovise, in Tampa, Florida in January of 1994. Throughout those years, he has primarily been involved in training, technical support, and product management for InfoSWMM and XP Storm. Since the merger of XP Solutions and Innovise about 1 year ago, Tony has been tasked with the management of the storm, sewer, and flood product family. In conjunction with Matthew Anderson and other team members, he has worked to improve the family of products and their integration. Carolyn joined Innovise in Broomfield, Colorado in January of 2013 and comes with valuable experience as she spent 5 years with a private engineering consultant assistant in water and wastewater master plans in the Florida area. At Innovise, she has primarily been involved in training, product management, implementation of services, and technical support. Matt joined Innovise in December 2016 and comes with very valuable experience, especially for today's webinar, as he spent 6 years with Autodesk, most recently as a product manager. He spent over 16 years as a private engineering consultant, and over the past decade, he has been involved in improving the workflows and technology that engineers use to study and design civil infrastructure and water resources. Thank you again for joining us. Would you like to start our discussion, Tony or Matt?
Let's go ahead and launch a first poll here. One of the things before we get into the agenda, I just want to ask you, at what stage is your current sewer master plan? Okay, are you at the state of data collection, or maybe you just have built a GIS foundation, but you really haven't done much with the data? Or have you taken that step of taking all of that GIS information that you've collected and begun to identify and build a hydraulic model of let's say 90% of those trunk sewers, a certain size and higher? Maybe you've calibrated that model within the last 2 years, potentially with a wet weather flow at a smaller diameter, included more sewers. You could have tested alternatives for future conditions, maybe form some capital improvement planning. Or maybe you've taken that step and begun to live model, begun to utilize SCADA information and to do some predictive maps. All right. So we've got a little different than the morning, but 60% of you are really just at that data collection or the GIS map area. But a good 14% of you have stepped into live modeling, which is a good ratio in between there. Okay. All right. So we want to, keep this, take this opportunity in the webinar just to begin to describe, some of the collection system master planning, some of the tools that Innovise has to assist you. Either, maybe you're a system manager, maybe you're a consultant tasked with that effort around your sewer collection. We see as Innovise, the concept of a digital twin being an important concept. So we'll introduce you to that topic. We'll talk a little bit about how to build a digital twin of your existing system, help you plan for some future growth, or assist you in your management and maintenance of that master plan. hopefully saving some scant resources. To do this, I think we're going to look at InfoSewer, as well as InfoSWM, and how those two tools will help you in that capacity. So what is a digital twin? As a father of twins, a digital twin is our representation of that physical asset, typically that's hidden underground. We've created a digital element. Okay, this concept dates back to maybe 2002, but Gartner, a research and advisory firm, has put that in the last 2 years as one of the top 10 strategic technology trends in 2017 as well as 2018. It's something that has increased steadily year over year. Wikipedia indicates it's just a digital replica of the physical assets, the process and systems that can be used for a variety of purposes. And I think that's the one element that we want to talk about, is how in that short term, how that digital twin can help us not only with what assets we have, but how those perform and how operations and what we can do to provide insights into that. So let's talk about that maturity. Okay, we asked that initial question: where are you? What stage of those elements are you at? And that first stage is that kind of that corrective stage. You're collecting data. You're determining what you have in the ground, where you have it in the ground, and probably in the corrective aspect, looking at, and reacting when a problem occurs, going out and having to fix it. The next level, kind of a preventative stage, really that quinquennial hydraulic model calibration, the master plan that we do once every 5 years. It's a snapshot, it's printed reports, it's spreadsheets. We've modeled our system to identify really where the bottlenecks are, and hopefully identifying where those are. The next step would be to jump into what would be a predictive stage. You're managing your assets. You're looking at your overall life cycle costs. You're doing some operational analysis, the pumping stations, the lift stations. You're looking at roughly your mean time between failure and attempting to reduce that. Or shortening that mean time to repair by proactively or predictively identifying where those failures may occur. The last step, we'd call that the adaptive level. We're actually using live modeling. We're continually simulating and operating. We're identifying those real-time impacts of field actions. So we're shutting valves off, or we're turning pump stations and changing things off, so that digital twin helps us understand our current activities in that phase. So that's something that we want to look at from a digital twin maturity, and how does that play out in your community?
Thanks, Matt. That was a great definition of digital twin. When thinking about master planning, I've seen that each master plan is really unique compared to the utility or the city that's involved. They all have their own goals and visions. Some might be technical, some might be more public facing and addressing the issues of the day, sometimes political as well. The regulations that the state, federal even, regulations are going to come out in that master plan in the way that it's been set up. For example, we have a local report that indicated that they pursued their master plan for the following reason: a new hydrologic and hydraulic model and the guidance on the capital improvement needs of the collection system are required as part of a prudent planning for the future and for the continued reliable and effective sanitary service to the community. One item to note is that we've heard from our asset management folks here at InfoSWMM and the people that we've reached out to in this market, and they've mentioned how important it was to have active master plans and asset management plans so that they were able to get better bond ratings and have a lower cost when it comes time to putting in their capital improvements. When they go to get the monies, they got much better rates if they had very current active management plans for their sewer systems. Here's an example of a master plan presentation for Charlotte County utilities, and I noticed that it was quite diverse. For example, they were looking at water quality. So an area that's got impaired receiving waters, perhaps water quality is going to be a big component of it. In another case, this is pretty common, looking at the prediction, the stresses on the system for growth, population growth, but even the fact that different parts of the land use are going to be built out and sewered, and that they weren't sewered before. And of course, ultimately, all of this master plan is used in that financial analysis that needs to be performed in order to make the improvements and keep high levels of service. A sanitary sewer master plan, as we've talked about in that progression of the digital twin, it's going to start out with a physical condition of the network. The assets are going to be built, hopefully built into a hydraulic model, go beyond GIS. The reason that's important is there's a new level of quality in the data that I find once it gets into a hydraulic model. A hydraulic model is going to impose on the system that the data makes sense relative to each other. For example, there isn't anything wrong with a 36-inch pipe as a value for that field. However, if it was connected upstream and downstream to a 12-inch, it's probably a data entry error. And it wouldn't be called out until you've put it into a hydraulic model. Perhaps it will give a very strange result, or maybe even an error or a warning message. So we really like that the data gets into hydraulic models and it gets further fine-tuned. Of course, the sanitary sewer master plan also comes into play for assessing the current state and then setting maintenance programs in place, and then using things like scenario manager of models, then we can look at future planning for that capital spending. At InfoSWMM, we have several products that operate in what we call the storm sewer flood family. This webinar, we're really concentrating on two of them though. We're concentrating on InfoSWMM and InfoSewer. We've got Carolyn on with us to do some presentations of both InfoSewer and InfoSWMM along the lines of our subject today of master plans. The first step, as I mentioned, was, and the base is really collecting the asset information, what and where, and then taking it into a hydraulic model and evaluating it based on infiltration and inflows, the loads that go on this system. The infiltration inflow being the wet weather loads, they're more transient, right? We have dry weather flows, but we have wet weather flows as well. In this image that we've captured from, actually this is local, this is Oregon City, not far away. In fact, Matt lives nearby, I think just one side of the river versus the other. We've gathered this, and you can see, for example, in this one that we've got some areas that are modeled, the ones in green, whereas the smaller sizes, they've been excluded from the model. I mean, they exist as part of the asset registry, but they're not part of the model. And I would say that this is something that I've seen over my time at InfoSWMM, that perhaps for financial reasons or model limitation reasons, that we just model the large trunks and we don't model all the others. I would think that over time this should diminish because of the ease of building models. The computers are so much faster, we can include all of these, and it removes the engineering judgment that we have to impose when we just do a skeletonized model. Because a skeletonized model has to include all the loads upstream, and perhaps if it's even more refined, it will even include some aspect of all of that pipe storage that's upstream as well. I would want to push people to doing a better job, including everything, so that ultimately when we are starting to identify problem areas such as surcharge or flooding issues or lack of freeboards, so perhaps there's risks of basement flooding, that this estimate is more accurate because we've made less engineering judgment and maybe some false judgments by excluding such big parts of the network. In the end, and something that we see almost in every master plan, is kind of a table of what's happening. For example, this table has capacity terms, and it's outlined places where the capacity is more than 100% in red. You know, as far as presenting to non-technical people, this is great. They can say, okay, these are the places where we have issues. Maybe it's an issue with the manhole. At the upstream manhole every link, we're looking at the depth of flow to the diameter of the conduit. Obviously, a D over D value more than one means that it's surcharged. And that's usually an issue in a sanitary sewer. Really over 50% full doesn't leave us a lot of capacity for wet weather events that may come. So we like to keep the, and even future growth. So instead of, changing the pipe size every 5 years, which is quite expensive, you may anticipate based on your planning areas of growth, and initially perhaps you have really low D over Ds, 10, 15, 20%, and then ultimately after several 5-year periods, perhaps you're getting more to the full capacity of the sewer system. So what we're going to do is we're going to turn some time over to Carolyn to do a demo, especially based on this idea of building the model from GIS. She's going to do this in InfoSewer, and an InfoSWM demo will follow later on in our webinar. She's going to demonstrate importing this information through a GIS gateway, which is a common tool to InfoSWM and InfoSewer. Look at allocation of loads, and then in a scenario situation, she's going to allow us to see a comparison of what will happen after we build out an area, looking at that idea of growth. So let me turn over and make her the presenter.
Thanks, Tony.
Carolyn.
All right, can you see my screen?
We do.
Okay, great. So I am going to do a quick demo in InfoSewer to show, as Tony said, how you can use an existing model and then build in a future system and basically compare capacity in your system. So InfoSewer is a fully GIS integrated program that is used in the planning, design, analysis, and expansion of sanitary sewer collection systems. This model right here is the city of Utica in New York. And this is a small portion of their system. They have 2 outfalls here in the system, and we're basically going to focus right here in this area just to see if we add in a future system here, a future development, if it's going to impact the capacity of our existing system. So first, I just want to run a simulation of our existing scenario and take a look at our results. So right here, I opened up the Run Manager. You have the ability to run a steady state simulation, a design simulation, and EPS. And I'll get back to what design simulation is later. I'm going to run an extended period simulation using our diurnal pattern and take a look at what the capacity in our existing pipes are. So I have a successful run. A couple of things we can do to take a look. My the number one thing I usually do is go to our range gravity main report. And what this does is it will take a look at what our maximum flows, our maximum D over D are. So right now, if I sort through my D over Ds, you can see the maximum D over D I have is 0.743. So basically, we haven't reached a full capacity of 1 yet in our pipes. So our existing system looks pretty good so far. So what I want to demonstrate is basically implementing a new development into InfoSewer. So future mains and future manholes. So it might be a little hard to see, but this new development here is on the top right. And what we're going to do is going to import that into InfoSewer and then allocate demands to it and then run the simulation. So we have a tool called GIS Gateway, and GIS Gateway basically helps create our models and continue to update our models based off GIS information that might be updated in the future. So right now I have a future manholes layers already added into as a cluster, and I'm going to add a new cluster for our future sewer lines. So basically what I do is I have to fill out the cluster information. Basically, I'm creating a connection to the shapefile and then setting up the parameters. So my first step is to set up that connection, then choose what type of object I'm bringing in, which would be pipe tables. And then what's really important in the GIS Gateway setup is having a unique ID that it correlates between the GIS and the InfoSewer model. So when you're first creating these models, it's really important to go through the process of coming up with a unique ID for each element in your system. The next step you can do is also bring in any information from your GIS. So if you have good GIS information, that might mean you have diameters, you have invert elevations, year of installation, material. So all that information can be imported into InfoSewer. And this tool here will allow you to map over that information. So if I want to map over diameter, I can select diameter in GIS and then diameter in InfoSewer and map that over. I can also use AutoMap, which would automatically bring in any GIS fields that have the same name as they do in InfoSewer. So if I select AutoMap, it will automatically map all of those fields into InfoSewer. So taking it one step ahead is if you have an existing model already created and you want to update that information based off information in your GIS, then the update existing records and delete non-existing records is what you would use. Basically, it's going to look for an ID in the GIS and an ID in the InfoSewer. If it matches, then it will basically update any information that you've brought into the field mapping for that object. The delete not existing records is basically if you have deemed a pipe abandoned in the GIS and you want to make sure that that's updated in the model, you would then use delete not existing records. And what it does is if it doesn't see the ID in GIS, then it will delete that object from the model, which allows you to basically delete out those abandoned pipes and then re-import the new replacement pipes. So let's select create new records and do that one more time, that pipe table. I must have clicked out of it. So let's AutoMap. So let's select future main. Okay, and then we'll click load, and load is basically now we're telling it, so let's load these shape files in. Okay, So it looks like our manholes were not imported. So what we're going to do is we'll go in, select edit, create new records. Oh, I had changed this to manholes. So let's delete these pipes. Okay, let's try that one more time. So we'll go back into GIS Gateway, and basically what I'm doing is just making sure there's no duplicate IDs and re-import. So that was successful, and if I zoom out, it should add in, did I not change that to pipes? Let's third time is a charm. So let's try that one more time. Make sure that I have manhole selected here and future manhole layers. So that's what I ended up changing. And then let's make sure we have edit pipe tables. Perfect. Okay, let's load that in one more time. Okay. So now if I go into each pipe, I can see that I have all my diameters, lengths, inverts. If I look at my manholes, I have no diameters or rim elevations added or any loads. So we first have to implement that into InfoSewer. So the best thing to do would be create a query to then establish what is the future system. And this section here is our future development. So what I brought into the pipes were year of installation. So let's create a query for year of installation. So basically I'm creating this query to pull into the domain all pipes that we're deeming as going into the ground in 2018. So if I add that in and validate it, I can press save, okay, and then I can add that to the system. Make sure we have those year of installations. So if we go to so we are in an existing space scenario. So now if we go in and add that into, that should add it into the domain. And domain is basically a selection. So now I want to select those connected nodes. And we're going to go ahead and run our fill link connectivity, which would then connect the endpoints of those pipes to our manholes. So when I go in and select connected nodes, that will then add it into our system. So now I can basically create a selection set that is all of our future system. Load the domain, say okay. If I clear that and add it, you should see it still adds up. So now I need to go in and add in that manhole information for that future system. So I'm just going to basically group edit and put in 4-inch diameter, and then I'm going to add in a rim elevation of 630 feet. So the last thing I have to add in is basically my loads. So I have no loads for my future system. So what I'm going to do in the purpose of the demo is basically use meter information and allocate the demands based off the meter information. And I'm going to use our load allocator tool that comes with our suite extension. So the load allocator tool pulls up a toolbar, and in this toolbar there's several allocation methods we can use. I'm going to use closest pipe, which basically says it's going to allocate to the closest pipe and then either evenly divide it up to the manholes or basically allocate it to the closest manhole, which is what I have selected here. I also want to select apply to pipes in domain and assign loads to manholes in domain, because what this does is basically not override any of the loads I have in my existing system. I just want to upload any loads to my future system. So I'm going to select future meter. I'm going to select dry weather flow, which is where my dry weather flow is applied in the GIS information, and then apply this pipe field. And the pipe field, what it basically does is it will tell in the meter file, it will input what pipe that meter was allocated to. So you can go in and change that later if you'd like to. So I'm going to press allocate loads, and you can see I have about 1140 GPM of dry weather flow that was applied to my future system. So now that I have done that in my base scenario, my next step is to then create a future system scenario. So I have an existing system scenario already created. So my future existing system, let's check to make sure the nodes are okay. So let's make sure that they are connected properly. So let's go into our existing scenario and take a look at this existing system. So I'm going to go ahead and run the simulation, and I think our allocator demand node. Oh, so let me close that and reopen this. Sorry about that. So basically, I'm going to do that really quickly and import that information one more time, and then I'll get that So if I switch to future main pipe tables, ID, and map over everything, and let's make sure that all the fields are mapped over. That's perfect. And then we'll load. Okay, so our future system is in place. And what I want to do is basically switch back to base and then our existing system. And that turns off all of our system here on the right. So what I'm going to do now is then create a future system scenario that will then activate this future system. So if I go into my scenario explorer and I create a copy of my existing system and then create a child to the base, I can call that future system. And then activate that scenario. It's using the query set that the facility manager had. So what I first need to do is go into that existing query and then create a future system. So I'm going to add in my existing pipes because obviously I want to bring in those pipes. And then I would create a future pipe layer like I did before and add in just the pipes that were brought in year of installation in 2018. Save OK, and now I have a future query set. So then I can go ahead and activate that scenario. And you can see that now all the pipes are now active for that system. So if I go ahead and I run the simulation, I should see now, actually, let's make sure that I added in all of the loads. I don't think since I closed it that I have loads added in. I don't. So let's go run through that allocation code one more time. Allocator. So we'll select dry weather flow and allocate demands. So I'm going to go ahead and run that simulation. And now we can go ahead and look at a report manager and take, oh, I ran steady state. So we want to run EPS simulation. And then we're going to go into the EPS range gravity main report, and then take a look at the D over D. So you can see here we have 3 additional pipes or 3 new pipes that have reached capacity in our existing system. And the best way to look at that is in a selection set that we can create based off those 3 pipes, and we can close this table, go into the selection set and press add. Make sure there we go. So it shows those 3 existing pipes that now have reached capacity because of our future development. So we can also go take a look at the outfall pipe directly connected to the outfall and see where we are in capacity with regards to the new development. So we're going to add in that existing system and then press OK. And so if I select this pipe here and I go to the graph, it will show me a graph showing me the D over D over time. Then I can go ahead and select my future system, and you can see that I have a little bit of increased D over D at that alpha. I'm still looking good, but that future development has added some capacity to that pipe. So the last thing I wanted to show really quickly was after you've basically gone through that exercise and seen that you do have pipes that have reached capacity, you can then basically use our design tool that will basically select based off an analysis criteria. So 12 inches or less if the pipe is above 0.5 D over D, then it's going to pull that in as a pipe that needs to be replaced. Then you can use your design D over D, which basically says you want to design the new pipe to be within these capacities. And then the replacement cost curve will then give you a cost per linear feet that will cost out how much it's going to cost to replace that pipe. So if I go ahead and press run and I go into my run manager and I select new, I have a new report that's created. And then I can kind of take a look at that. So you can see here that pipe 228 is saying the InfoSewer is recommending that it should be replaced based off that D over D analysis pipe. And the replacement pipe should be 12 inches, and the total cost for that pipe should be about $16,000. So I'm going to turn it back to Tony to continue going through InfoSWM.
Great, thanks for that InfoSewer demo. Actually, I didn't really mind the repetition because I'm pretty new to it, and it really makes me think about how awesome the scenario manager is. I mean, we use a scenario manager for future conditions all the time. It's just really quite logical, but I see the scenario manager that's in InfoSWM and in InfoSewer as really being a tool where you can be quite creative. So not only do we look at just population growth that we're tying in a new system, but it could be quite diverse. For example, let's say you have an area that has a lot of septic system failure. There's a lot of groundwater contamination because of old septic systems. You're deciding, okay, we're going to sewer this area. We're going to try to make some improvements. Well, it's quite easy to, allocate loads like we've shown and, get a handle on that. For example, what about patterns in the flows? Let's say you have an option, send the sewage to a regional facility or one of your own that has capacity. Maybe they've got different costs per million gallons that you're treating. Well, if you could add lines and divert, then this is really going to be beneficial. A scenario where you're just changing flow directions, for example. A real common thing might be pump station optimization. One of the most expensive things to do is operate pumps. Well, if you operate them better at different times of the day with some controls, or you're going to operate them less often by having more storage in the wet well, this is a great scenario. Even the fact that you could be looking at aging infrastructure. I'm kind of waiting to see this. I really want to, I haven't yet. I'm sure it's out there, but what about in those 5-year build outs, you also decay the quality of the sewer over 5 years, right? A 30-year-old sewer doesn't perform as well as a new 5-year-old system. So we've talked a little bit about InfoSewer, you've seen a demo, but we also have InfoSWM. How are they the same? How are they different? Well, I just have a few things to mention about that. So they're both obviously for sewer collection systems. On InfoSWM, it has a much stronger stormwater component, many different hydrologic methods that can be used. While both of them operate as a full GIS integration, an extension to ArcMap, and can handle city scale models, it's really down to the hydraulic analysis as well as perhaps the ability to handle stormwater in a sophisticated way. In InfoSewer, it was a steady state peaking factor type approach. It's really good for sewer systems, the design of them when you're not expecting lots of levels of surcharge. On the case of InfoSWM, InfoSWM is using the EPA SWIM engine, SWIM 5, and it is being able to model full dynamic waves. So the storage effects of conduits, system backwater, flow reversals even. So if it's a complex sewer with lots of loops and so on, then InfoSWM would really be the most appropriate product for you. So we're going to tap Carolyn again for another short demo about InfoSWM. And in this InfoSWM demo, we're hoping that we can also present to you a little bit about not only the dry weather flow, which is somewhat similar between them, but what happens during wet weather events. We use the technology called RTK, which is 3-unit hydrographs based on rainfall. So we're going to show you that. And in fact, that is a real specialty work in sanitary sewers, doing a good job on RTK. We even have a tool specifically for that called RDI Analyst. So one more time over to Carolyn. Let me make the presenter again. Thanks for doing this. This is great.
All right, can you see my screen?
Yep, no problem.
Okay, great. So I'm going to show a quick demo of InfoSWM and basically setting up scenarios, applying dry weather flow and RTK, taking a look basically how we can do the same thing that we did in InfoSewer and InfoSWM, but a couple more capabilities that we might have in InfoSWM. So InfoSWM is a fully GIS integrated software just like InfoSewer. It's comprehensive hydrologic, hydraulic, and water quality simulation software that is widely used for management of urban stormwater, wastewater collection systems, and custom and combined systems. So this system here is in Naperville, Illinois, and the downtown area, which is on the left-hand side of the system, is basically a combined sewer system. And then the right east catchment area on the right is just sewer only. So we're basically going to focus on that side and just applying dry weather flow and RTK and taking a look at what we can do there. So we have a few scenarios set up here in InfoSWM, and one of them is our sewer only. So that's basically set up just how it was in InfoSewer with a query set that will basically just activate our sewer system. So if I reset map display, you can see here the left side has been now deactivated, and I can go ahead and turn off that aerial so you can actually see. So one of the things before I start this I want to talk about is that you can actually import InfoSewer, H2Map Sewer, and InfoSWM or H2Map Swim directly into InfoSWM. So if you have an InfoSewer model that you then want to apply to InfoSWM, you easily can import that. There's just a few things that would be you would want to look at while you're doing that import. The first one is just flow units, making sure that flow units are set up the same way that they are in InfoSewer, and that would be here where you would select the same. So any loads, if the loads are in GPM in InfoSewer, you want to make sure that they're in GPM, that you have GPM selected here in InfoSWM, because it won't automatically convert it. You want to make sure that you have your pump settings set up properly in InfoSWM that correlate with InfoSewer. If you have any short pipes in InfoSewer, you can then use our conduit, time set for conduit lengthening option. So you'll want to use that, and our default is 5 seconds. And then the best thing to do to compare that everything's been imported properly is to run both of the models and then compare system loads in InfoSewer to total inflow in InfoSWM. And that'll give you a good understanding that InfoSewer has now properly been imported into InfoSWM. InfoSWM also uses an enhanced form of the latest EPA swim simulation engine, and it uses these process models. So basically, if you're just doing a sewer system in InfoSWM, you can remove rainfall runoff and just select dry weather flow, RDII, external inflow, and flow routing. So it basically will just run these process models and take a look at those models while you're running the simulation. You can also set up, you can also use, if you're doing stormwater modeling, runoff model within the simulation option, as well as what infiltration option you're going to use here, as well as the routing model. So it's wildly populated to use dynamic wave, which takes into consider backwater condition in your system. So we recommend using dynamic wave in InfoSWM. So if I close this and I go ahead and run my simulation, I will now have results just for my sewer system here. So let's take a look at, what we're seeing in what information we actually have set up on our manholes, and then take a look to see if we have any flooding in our system. So if we go ahead and I select a manhole, the way that dry weather flow is applied to InfoSewer is applied to the manhole hydraulic table. And you have about 10 loads that you can apply in InfoSewer. It's a little different applied in InfoSWM, where you would select the hammer tool drop down, select inflow, and then you have 3 tabs. The first tab is external flow, dry weather flow, and then RDII. So you can have a RDI RTK hydrograph applied for each manhole. And you would apply basically a rain gauge, so that's your observed data, and then your RTK parameters that you have calibrated specifically to the observed data that you have for this manhole. Then you can go in and apply dry weather flow. And so you can see here you can have multiple rows or dry weather flow applied to each manhole. And in this case, it's because we have a couple weekday and seasonal. But if you had, let's say, a residential flow, employment, commercial, you can all set that up with its own allocation code, its own dry weather flow. And then input its own pattern there. So you have 4 patterns that you can implement to each dry weather flow. So that's how that information is applied in InfoSWM. And if we go ahead and we look at our system, so now let's do a little analysis and figure out if we have any flooding in our system. So I'm going to use a map display option here, and I'm going to just classify 2 breaks. And I'm just going to see if we have any flooding. Obviously, it's a sewer system, so any flooding is bad. So let's apply this with a red. So anything that's higher than 0.001, we're going to apply. So you can see we have 4 locations in our sewer system that are experiencing flooding. So we can look at that in a couple different ways. So if I select the manhole and I open up my graph, I can select flooding, and you can see here that halfway through my simulation, I start to experience flooding, which may be because my pipes are too small in that location. The other thing I can do is actually go into my report manager, select new, go to my graph report, select hydraulic profile, and then I can basically go in and select my manholes, say open, and it will open up my hydraulic gray line. Now I can actually play a little video to show how my flow is flooding. You see here in junction 76 and 74, I get to flooding a little earlier than the rest of the system. So basically at this point, we got to figure out what size pipes we need in this location in order to remove this flooding. So I'm just going to focus right here in this area, and let's just create a new scenario, upsize these pipes, and then rerun the simulation and see if we remove the flooding. So let's take a look. So our existing pipes in this area are 6-inch, and we have an 8-inch here. So if we want to upsize, let's just go with 12. That's upsizing the pipe pretty high, but we obviously want to do that to any downstream pipes in our system. So what I'm going to do is I'm basically going to use my domain manager again, and I'm going to select in my domain that pipe segment. So let's just select. It's all in the domain, say selection set, just like we did in InfoSewer, and say replacement. Say okay, load it, say yes, and then okay. So now we're just going to create a new scenario. And if I go into my scenario explorer, I can basically copy this. And this time I actually want to create a child to this sewer only, because I want all of the information that that sewer only scenario has I want my new scenario to inherit everything that sewer only scenario encompasses. So I'm going to paste child and call it CIP, Capital Improvement Plan. So I'm going to go ahead and activate that, and basically now it did not like that. Let me reopen up InfoSWM. Sorry about that. So basically what I'm going to do is I'm going to create a new scenario called the Capital Improvement Plan. And now in InfoSewer, I just showed you that you would create a new facility to basically activate these pipes. I didn't really change anything in the existing system, so I didn't need to create a data set. But in this case, I would have to create a data set in order to change what those pipe diameters are. And I want to keep the integrity of the sewer only scenario. So I don't want to change any information in that scenario, but I want to create a new scenario, and I want to analyze whether upsizing those pipes to a 12-inch will remove that flooding. So I'm going to go ahead and claim. And it's going to take me back to where I was before. So let's close this and bring on all my tools. And I actually accidentally selected that subcatchment. So let's reapply this replacement. And if I clear this and add it, it shouldn't bring in my subcatchment anymore. So what I'm going to do is I'm going to go back into my scenario explorer, and I am going to activate my base and go into my CIP. So here I want to create a new data set for conduits so that I can apply new diameters to that pipe segment and not change it in the sewer only scenario. So I'll clone my active scenario and call it CIP. So say OK, and then if I go ahead and activate that, then I can go back into my scenario. So now I'm active in CIP scenario with a data set called CIP. So I'm going to go into my data table, select domain, and it's going to bring up just those pipes that I've selected in the domain. I'm going to go over to geometry, and I am going to upsize those. So this is in feet. So I'm going to set it equal to 1. So that would equal 12 inches. So I'm going to save that. And then now basically I'm going to go in and just run the simulation and see what that impact will do in this area. So if I go back into my map display and I set up that you can see already the groups that are set. Now I don't have flooding in that area anymore. I still have flooding in this one spot that I would have to look into. But let's go in and look at the hydraulic grade line again. And let's change this to 5 and play it. So you can see here my pipes don't even surcharge. So we've taken care of the flooding in that area by creating a new scenario, creating a new data set, and then rerunning that simulation and taking a look at the results. So I think now Tony is going to take over and talk a little bit about RDI analysts and how you can calibrate observed data and then basically implement those RTK parameters and push it back into InfoSWM.
Great, thanks again for excellent demo. I will be a little bit brief on this just for the sake of time because I realize we've used up our hour already. By RTK, we're talking about triangular unit hydrographs that relate the rainfall to how much flow is going to be in your sewer. Essentially, you want to have a really good fit. So you kind of want to end up where there's a good relationship between the rainfall and how much RDI flow you have. Well, the process in the RDI analyst is to take in flow metering data, and in that flow metering data, you want to get it down to what's dry weather flows, and with that rainfall period being covered as well, obviously you know when you have dry weather periods and when you have wet weather periods. You can extract essentially a dry weather flow and then develop a dry weather flow pattern. And this input then gets derived into this pattern. Here's the shape that we're talking about, like hourly peaking factors. And we create the RTK response. So this blue is the corresponding RDI flows from creating RTK parameters based on the rainfall and having extracted the dry weather flow out. This is a powerful tool. Other tools exist. For example, EPA SOAP, it's similar. But this has been integrated with InfoSWM in such a way that you end up with the RTK parameters that yield a good fit. It does it by running many tests and then evaluating the goodness of fit. And so you end up having, with your observed and your calibrated, you can visually see through all of your sets of RT and K parameters which ones are good ones to use, because the wet weather response in a sanitary sewer, especially an older sewer of certain materials, can sometimes be significant. Like I've heard of 10 times dry weather flow in the worst of sewers. So it's not something that you should just ignore and think all my sewers are tight and they don't have any infiltration and inflow. So in the end, you end up with RT and K parameters and perhaps optional abstraction and storage values as well. You give it a range for its iterations, and you can use those in your model. And on behalf of Carolyn, Matt, and myself, we really appreciate your attendance. We've really enjoyed presenting this topic with you, especially in older. Can sometimes, I've heard of 10 times dry weather